In the last part we met molar conductivity, how well 1 mole of an electrolyte carries current. Its symbol is lambda, and it equals the conductivity divided by the concentration. Today we will do something simple. We add water to the solution. This is called dilution, and it lowers the concentration. Let us see what happens to the conductivity and to the molar conductivity. First, conductivity. Conductivity looks at how many current-carrying ions sit inside one small unit of volume. Lower ions there means a higher conductivity. Now add water. The number of ions stays the same, but they now spread through more water. Though that same small volume now holds fewer ions. Though on dilution the conductivity always falls. This is true for both strong and weak electrolytes, for the same reason, fewer current-carrying ions in each unit of volume. Now molar conductivity. This does not look at a small volume. It looks at all the ions made by 1 whole mole of electrolyte, however much water they sit in. There is a relation joining the two. They saw that molar conductivity equals conductivity divided by concentration. Whole volume holding 1 mole we can call the volume by. So we can also write molar conductivity equals conductivity times the volume. Now see what happens on dilution. The conductivity falls, yes, but the volume holding 1 mole rises a lot. Experiments show the volume rises more than the conductivity falls. Though on dilution the molar conductivity rises. But first this seems strange. Adding water lowers the conductivity but raises the molar conductivity. Both are true, because they measure two different things. Now keep adding water, until the concentration comes close to 0. Then the molar conductivity rises and rises to a largest value. This largest value, reached as the concentration approaches 0, is called the limiting molar conductivity. Its symbol is lambda 0. It is a fixed value for each electrolyte. Then the concentration approaches 0. The molar conductivity is known as the limiting molar conductivity, lambda 0. Now an important difference. Bomb electrolytes split almost completely into ions in water. These are called strong electrolytes. Sodium chloride and potassium chloride are examples. In a strong electrolyte the ions are already all out, so dilution brings no new ions. The molar conductivity still rises a little, because the crowding between ions eases and they move more freely. Though the rise is small and slow. This slow rise fits a simple equation. Molar conductivity equals limiting molar conductivity minus V times the square root of concentration. Here V is a constant. Here is the special thing. If we plot molar conductivity against the square root of concentration, we get a straight line. Extend that line back to 0, and the value where it cuts the axis, the intercept, is the limiting molar conductivity. The slope of the line is minus V. This constant V depends on the type of electrolyte, that is, on the charges of the ions. Sodium chloride is a 1,1 type. Calcium chloride is a 2,1 type. Magnesium sulfate is a 2,2 type. All electrolytes of the same type have the same mass. Now a beautiful idea. Kohlrausch, a scientist, noticed that in the limiting molar conductivity each ion gives its own fixed share. That share belongs to the ion alone, and does not change whatever its partner ion is. Kohlrausch's law of independent migration of ions states that the limiting molar conductivity of an electrolyte is the sum of the individual contributions of its cation and anion. In the equation, the number of positive ions times each one's share, plus the number of negative ions times their share. That is, the limiting molar conductivity equals the positive ions share plus the negative ions share added together. Each ion's share has been measured and put in a table. For example, hydrogen plus gives a very large share, and hydroxide minus is also large. Using these we can add up the limiting molar conductivity of any electrolyte. Let us do an example. Calcium chloride splits into 1 calcium 2 plus and 2 chlorine minus. Though its limiting molar conductivity is 119.0 plus 2 times 76.3, which is 271.6. Similarly for magnesium sulfate, 106 plus 160, which is 266. Though the other type, the weak electrolyte. Things like acetic acid split only a little into ions in water. The rest stay as whole molecules. Though at normal concentration there are few ions. Though diluted, fear something new happens. As the water increases, more molecules split into ions. That is, the number of ions itself grows. Though the molar conductivity rises steeply and quickly, not slowly like a strong electrolyte. This creates a problem. Because the weak electrolyte's graph shoots up steeply near zero, we cannot extend the line to find the limiting molar conductivity. For a weak electrolyte we find it using Kohlrausch's law. For a weak electrolyte, the degree of dissociation, alpha, is approximately the molar conductivity at a concentration divided by the limiting molar conductivity. Full dilution, alpha approaches 1. We cannot measure acetic acid's limiting molar conductivity directly. Kohlrausch's law gives a trick. Acetic acid's limiting molar conductivity equals that of hydrochloric acid plus that of sodium acetate minus that of sodium chloride. When we add these, the unwanted ions cancel, leaving only acetic acid's ions. That is 425.9 plus 91 minus 126.4, which is 390.5. The number that measures how easily a weak acid splits is the dissociation constant, with symbol A. We can find it from alpha and the concentration equals the concentration times alpha squared divided by 1 minus alpha. An example. From the conductivity of acetic acid, its molar conductivity was found to be 48.15. Alpha equals the molar conductivity divided by the limiting molar conductivity, that is 48.15 divided by 390.5, about 0.123. Putting this into the equation, A comes to about 1.8 times 10 to the minus 5. Now the two big uses of Kohlrausch's law. First, if we know each ion's share, we can add up the limiting molar conductivity of any electrolyte. When water, which is hard to measure directly, later splits into one hydrogen plus and one hydroxide minus. Though water's limiting molar conductivity is the hydrogen plus share plus the hydroxide minus share. Second, for weak electrolytes, we know the limiting molar conductivity and the molar conductivity at one concentration, we can find their dissociation constant A, just as we did for acetic acid. Let us recap. Then we add water and dilute, the conductivity falls, but the molar conductivity rises. Largest value, reached as the concentration approaches zero, is the limiting molar conductivity. A strong electrolyte rises slowly, and we read its limiting value of a straight line. Weak electrolyte rises steeply, and needs Kohlrausch's law. Nachine gives its own share. Alpha shows how much has split, and A shows how easily it splits. That is everything for today. If you liked the video, please like and subscribe to the channel. Thank you.